Okay, good evening, good afternoon, good morning, and if you have different time zones, okay. My name is Heng Gang Lee. I am a senior structural engineer with City of Toronto. I will be the host for tonight's seminars, okay. We are honored to have Dr. Tedros to be our guest speaker for tonight. And I guess, in civil engineering in this field, a lot of people know Dr. Tedros. He is an international authority in the design and technology of girders and precast prestressed concrete structures. His reputation for engineering innovation is worldwide in academia and civil engineering and structural engineering circles. And the best known Dr. Tedros innovation is new girders, which is widely used over the world. I think now in Ontario, we are using new girder also, and MTO pretty much like the standards. As an international research, and Dr. Tedros is the author for 18 patents, 1 book, and more than 200 journal papers. And he is the 4 times T.Y. Lin Award winner and unprecedented. And this award, T.Y. Lin Award, which is jointly given by ASCE, ACI, and PCI. So without further ado, and I will give the time to Dr. Tedros. Dr. Tedros.
Thank you very much, and thank you all for inviting me to speak to you this evening. I was telling the guys just before we got all connected that I received my doctorate at the University of Calgary, and I'm very, very proud of that. I had good education, and I will not forget it. So I'm going to try to get my screen on. I hope everybody can see it.
Yeah, we can see it. Great.
Okay. So this gives a summary of a project that was sponsored by PCI. My company, Construct, which I formed after I retired from the university, jointly with WJE, University of Nebraska, NC State, Louisiana Tech, are organizations that help me with the research. Standard Concrete Products, Course Lab, Metromont, Concrete Technology Corporation, Tyndall, and FACA were the precasters that were the key players in this project. FACA carries the brand name of Dura from Malaysia. Jackie Vu is an authority, international authority, and he was one of the guiding people. We added Gage Brothers, and we have 2 steel forming company, Kasab Steel in the United Arab Emirates, and Hamilton Form that contributed to the project. The result of the project was phase 2 report, which was the final report, was published in September of last year. And the picture on the right shows some of the key authors of that report and contributors to the research. Part of that, this is a 750-page report. It is available. Anybody, I'm sure Philip can help facilitate that. You would need to call PCI or take a shortcut and talk to me, and I'll release it to you. If I get in trouble, Philip will try to protect me. It's supposed to be a report to members only of PCI. But I think it's kind of foolish. It should be distributed as widely as possible. The most important part of that report is the summary. It's called PCI UHP Structures Design Guide. And it's only 70 pages. There's another part that is Materials Guide. So that's kind of an overview. So the goals of the PCI UHPC research project was to get a rapid implementation of cost competitive, very, very important cost competitive precast UHPC buildings and bridges, building components, bridge components, building systems, and bridge systems. One of our goals is to train the precasters to use their facilities to produce UHPC without a whole lot of disruption to what you do day to day. We wanted to develop materials and structural design guides for people who want to mix their own UHPC and to design with it. The report includes worked out design examples to help train the designers. And the whole idea is to introduce the least amount of change to existing codes, whether it's AASHTO, ACI, or in your case, the Canadian codes. So what is PCI UHPC? We identified it with compressive strength and what we call tensile properties. Compressive strength at service, 120 MPa. At pre-stress release, because our focus is on pre-tension members. So at release of the pre-tensioning force, 70 MPa. Here we recommend this, especially for bridges, but we don't insist on it. It's not a requirement. The requirement is to define our UHPC is 120 MPa at service strength. For tensile properties, we go a little bit further because that's the most important set of properties. Tensile, not compression. Compression is easy to to talk about because that's what you're used to doing. Tensile properties are the most important, and they are important because we have fibers in the mix. So minimum, all based on the bending test for ASTM, and with a minimum cracking stress of 10 MPa, minimum peak stress of 14 MPa, and then we have strain hardening to make sure that once the specimen cracks, the stress continues to go up, the load continues to go up. That's strain hardening. If we don't have strain hardening, we cannot allow the design we're doing. We do not do strain softening. Also, ductility and toughness are represented by the last requirement. So I don't have to go very far with this. Everybody knows what UHPC is. Cement, silica fume, additional materials, probably lime in Canada is very popular, getting popular here in the US, metakaolin, slag, and then very fine silica sand. We use fibers. We don't insist on the very fine 0.2 millimeter by 12 millimeter or 20 millimeter, very tiny microfibers that are black steel but coated with brass. If somebody has other fibers that will give us the properties, they can use them. Of course, the chemicals that are needed to make it flowable and nice, good, clean tap water. Now, this slide, I think, is very important because some people are still debating what to do to establish tensile properties. So FHWA has been advocating for direct tension testing. We have been advocating for flexural prism testing. Split cylinder test has existed. And then there is a new testing program called double punch test that I think started in Spain, and Florida DOT is interested in, and others are interested. So the reason we chose the flexural prism test is that there is a standard for it. Everybody knows how to test a prism and flexure. Here, it's a little bit more complicated because we need to get load deflection diagram, not just load, not just the peak load. But it is something that people can use with their compression machines or some form of compression machine and test. And that's very important. It needs to be simple and it needs to have a standard. The direct tension test, Dr. Graybill has been trying for years now to get it introduced to ASTM, and he has been turned down. And now he has taken the route of trying to get a standard approved by FHWA or by AASHTO, and that is in process. The split cylinder test and the direct tension test, both of them have given high variability. The direct tension test in particular is very sensitive, very difficult to do. And here in the US, we only have a handful of university labs, no commercial labs that can do the direct tension test. While the flexural prism test, you don't need the machine, you need the accessory to apply the load to it. The double punch is very attractive in its simplicity. So it's a cylinder, and you have a void at the top, a void at the bottom, and you put a steel pin and a steel pin and push on it, and it splits it radially, and it creates radial cracks. And that gives an idea about the amount of tensile capacity it can handle. None of these is perfect. In our opinion, the easiest and the most reliable one is the flexural prism test. Some people may want to choose a couple of them, but keep in mind that you have precasters that you want to engage and not make life miserable for them. So they need to have relatively easy to use standardized test. So that's our choice. It's important to use ASTM 1609 as the main method for establishing properties. Throughout the project, we had 2 phases, and we had a collection of all of the prism testing, the flexural testing we've done. You could tell there's variability here, even though the prism is very easy to make and very easy to put on the side and apply the load to it. But there's still variability because tensile properties of concrete are generally variable. The good news is that the average is relatively high of these tests. The minimum specified standard is what we use to accept the material as meet the PCI UHPC requirements. And in design, we go even further than that, and we use the cracking stress, and we use the 14 MPa as the maximum, the cracking stress, 10 MPa as the maximum, 14 MPa is the maximum that we can allow in design, and then the ductility, which doesn't enter into our design, but it's required. So people will say, how do I be sure that my material that I'm mixing in my plant is satisfactory? What we're basically using the ACI, and I am sure that the Canadian code has something similar, and that's to mix a number of tests and to create averages and standard deviations, and based on the number of tests, you decide what you would design your mix for. Now, this is the important one, because that's what you do on a project by project basis. Acceptance testing has to be simple, and it has to be within the means of the precaster or the precaster's testing lab nearby. You cannot run and ship it to a university 200 kilometers away and expect convenient work, because sometimes you need to do the prism testing in 1 day, 3 days, 4 days. So it needs to be convenient and readily available. So the picture on the right is the prism test. That's probably the most difficult of all. There's also a cylinder test, very simple, convenient, but you have to grind the ends to get good results. And for the fresh concrete, we have to have a flowable mix. If we don't have a flowable mix, we would have trouble filling the molds. So the goals for production, it has to be practical to implement, it has to be cost competitive, and the precasters will need to tell us what works for them. We did develop guidelines in the report, but a lot of the precasters have their own way of placing the concrete, and we need to be open-minded and responsive to their expertise and their needs. This slide is a little bit crowded, but it shows a variety of products that we made in the project. On the top left, you have a building product for office floors with very large openings to house utilities and communication cables. And it's a composite, and I'll talk about it a little more. The one in the middle is a voided slab product for bridges, and the white color is expanded polystyrene foam to create the voided slab. The one on the top right is a composite of UHPC I-beam with UHPC deck, ribbed slab deck. And the bottom left is variations of the one on the top left. The middle is the variation of the one on the top. And the bottom right one is my favorite because that was the one that was made by FACA in Toronto, near Toronto, and shipped to NC State University, North Carolina State University for testing. It's a full-scale test, and I'll talk some more about it. Okay, this is my message. We cannot have cost-competitive UHPC without structural optimization. So this is a great time for structural engineers. Most of the work that has been done around the world ignored that second half of the package. Everybody is focusing on how to mix and how to get the highest possible strength. But unless you know how to use it in a real structure, then you're missing the rest of the story. So structural optimization is the key. In our mind, we have 3 criteria for structural optimization. It has to be simple, it has to be conservative, and it has to be cost competitive. And I mean cost competitive on a first cost basis. These are very hefty goals, but we strived very much to try to achieve them, especially when we talk about 2 conservative, 3 cost competitive, there's a clash there. And some people say you cannot have all these 3 conditions. Pick 2. No, we're picking all 3. And I'm sure just about everybody knows Steve Jobs and Sir Richard Branson. Both have the same message. Steve Jobs was a little bit tactful, diplomatic, in telling people that you start with something, it starts out very complicated, but you keep working on it and you can peel off the onion until you get a very elegant solution. Richard Branson is saying you're stupid if you don't do a simple design. My message is that simple is hard. A lot of people can come up with differential equations and very, very complicated solutions. I think that's kind of hiding the real simple solution that everybody should strive for. So cost effective. We don't want to have a cost-effective cross-section shape. Take the I-beam, reduce the web width, and say that's going to be my optimization. That will never work. You need to take a bridge or take a building and find where you can introduce UHPC in the most suitable, convenient way. For example, in the state of Minnesota, they use cast-in-place haunch post-tension slabs. I don't know about Ontario or other provinces in Canada, but the cast-in-place haunch post-tension slabs in Minnesota and Kansas are quite popular. You need to take that whole bridge deck and replace it with a 550 millimeter precast UHPC box slab. It will give you the deck immediately. It will not be interrupting the population around the bridge. It's good for a accelerated bridge construction. So that's on first cost basis, and that's what we should, unfortunately, that's what we should all try to do, because we all do the bidding and the lowest bidder gets the job. But there is also a lot of bonuses, a lot of additional benefits. Study in Australia shows that the expected life is more like 340 years instead of 75 years. It's good for the environment. because you use lower volumes of materials. It reduces shipping costs, it reduces foundation. And it is safe because sometimes you have a longer span without shoring. A lot of our partners in the project, in particular FACA, have done a terrific job. The product that FACA produced is very, very good, excellent. And Standard Concrete Products in Florida was also a very, very good product. The other 4 companies struggled a little bit, but eventually achieved their targets. There's one item at the bottom, post-cure thermal treatment, proves to be very beneficial. And I believe you in Canada tend to want to do that. We here in the US don't insist on it. If it's needed, we use it. If it's not needed, we don't use it. It adds 15% to the properties of the concrete. This is an example of what UHPC could be. On the right, you have a solid slab. You probably see the strands, 4 strands at the top and a whole bunch of strands at the bottom. You see a forest of stirrups end to end. You go to the left, you hardly have anything. You have the foam, white color. You have the 4 strands at the top. You have some strands at the bottom and a little bit of bars on the ends. That's it. That's all you have. So as engineers, the design is simpler, the detailing is simpler, the precaster benefits the same way. Although the base price of the material is high, but there are additional benefits. I'm going to show this slide that gives you the flowability of the mix. I did it too quick. As you could tell here, it is very flowable. Now we talk about flexural design. Everybody knows how to do service limit state. No issue. You need to use the creep and shrinkage coefficients for this material, determine pre-stress loss, and calculate using MY over I. No issues. Flexural strength is a little bit more complicated. I will first talk about flexural strength with fibers, and I'll talk about what happens if you ignore fibers. If you have pre-stressing and pre-stress member, the main tension element is actually the strands, not the fibers. So the strain diagram follows plane sections remain plane. The stress diagram before cracking is straight lines, triangles. After the product cracks, the strain climbs up. You still have triangle for compression, but then you have a triangle for tension just a little bit. Then it becomes uniform down all the way to what we set as the acceptable ultimate strain in tension, which is 500 microstrains. Beyond that, the section still works, but we're not going to give credit to the fibers to give any tensile capacity. And this diagram, stage 2, is probably the one that's used the most until you get to the very end, when the strain at the top is 0.003, or for you in Canada is 0.0035. It really doesn't matter. It's good both ways. And you use the equivalent rectangular block and use beta of 0.65 because it's very high compressive strength. So the 0.003 doesn't have to be that. It can be the 0.0035. And you create based on that, and we have a spreadsheet. we created in our company, and we're happy to share it with people who would want to call me or write to me. We create the moment curvature relationship. The moment rises up until a crack develops and the fibers start to pull out of that crack, and you could have a dip. But then it picks back up again because of the strands in the section until you get to the ultimate strain. If that's with fibers, if you have 0 fibers, if you take all properties but the fibers equal to 0, you get what's called MNB, which is not very different from MN2. So MN1 is an intermediate value, MN2 is the end value at ultimate strain or ultimate curvature. You get the first one, get the curvature corresponding to it, get the strain that goes with it, and determine the resistance factor. That's here in the US. I know in Canada you have materials resistance factors, which is a more elegant solution than the solution we use here in the US. So, but in the US, we would have the resistance factor here in ASHTO or ACI, multiplied by the nominal capacity, resistance factor here multiplied by the nominal capacity. If the first one is the high one, VMN1, then that's your strength. If the second one is the high one, that's your strength. It's that simple, the larger of the two. But item number 6 here, for longitudinal direction of pre-stressed members, which is the most important check, you can ignore the fibers, meaning that you can use whatever computer program you have at this time. Take an example. This was an example that was supplied by Dr. Grabia of Minnesota, IBM. He squeezed the web from, I think, 6.5 inches to 3.5 inches. I'm sorry, using US units. And he put a conventional concrete deck on it, which only has 4 KSI. That's like 4 times 7, 28 MPa, 4 KSI. Very, very low compared to the 22 KSI, the 152 MPa here. So he used that, and he came up with a graph on the left. And he says that point B on the graph is what determines the capacity. Point B on the graph is shown here at the bottom right of that picture. You note here that he decided that the strain at the bottom cannot exceed the critical strain that he calls, in this case, is 0.0045. Now, close to 0.005, but the trick here is that he thinks that you cannot go beyond this, which is the maximum strain in tension for the concrete with fibers. To me, that's a severe restriction, because when you do this, the stress in the strain is even less than the yield point. So in all of the work we've been doing for these 50 or 60 years, we will never achieve the ultimate strength of the strain, which to me appears to be a waste. If you use the PCI UHPC, again, the first point is similar to point B for FHWA, but we carry it all the way to ultimate. That's point B for the graph on the right using PCI UHPC. And if we want to ignore the fibers, we're not going to get much different from this. The graph on the left appears to show you low ductility, and that's only artificial. And when I asked one of his associates, why are you doing this? He said, because we don't feel good about the crack. So we stop at the crack. Well, you expect cracking, so I don't know what don't feel good means. Here in this chart, we are taking it all the way as we have been doing all the time. So as a summary of this is a very important slide. If you use the FHWA recommendations, use the dashed line, and it drops. I don't know how it drops. It kind of doesn't make any sense. If you use the PCI recommendations with the strands he has, which are 54.7-inch strands, it still continues to go up until ultimate. And it gives you about the same peak as the peak he gets from, but at a later curvature, later strain. And it's not needed. So if you take the whole section again, and instead of 54.6-inch strand, I'm sorry, 54.7-inch strands, you reduce it to 54.6-inch strands from 17.8 millimeters to 15.2 millimeters. You still get the capacity you need. That's 2/3 of the pre-stress that you need for the section. I would say thank God for FACA. They approached us even before the PCI project started. So that's how progressive they have been. They said, we want to have a modified NU beam. What can you choose for us? And they created a project, and we came up with what we call decked I-beam. Decked I-beam has a very wide top flange poured at the same time in the same production run with the rest of the beam. It is good for accelerated bridge construction because you don't have to form and pour deck at the field, at the site. It uses quite a bit less concrete, and it is excellent for long-term deck durability because here in the Midwest in the US, that's the biggest problem, is the deck. So if you take the example run by FHWA, and if you run it again using the PCI method, and run the same loads 1/3 time using the PCI UHPC with decked I-beam, you can tell here you only need 32 strands. You need no stirrups, 0 stirrups, and it's a very fast construction. So you save a lot on the concrete, you save a lot on the strand, you simplify production, and you get, that's how you get the cost effectiveness. So we've done a whole bunch of tests using products. And in all of the tests, we far exceeded the design capacity. Very quickly here, development lengths, we're piggybacking on what Dr. Gabriel developed, which is a transfer length 20 strand diameters, development length 40 strand diameters. Bars 8 to 10 bar diameters. For vertical shear, we're sold on what Canada does. We're sold on what AASHTO does. Thanks to Mike Collins and his associates at University of Toronto. He led the way back in the 90s, and we're very glad for that. So for conventional concrete, you just get the strain, the flexural strain. From it, you calculate beta and theta values that are used to calculate V sub C and V sub S. If you're doing UHPC, all the chance that you do is take VC out and replace it with ZCF, representing concrete mixed with fibers. And because of the minimum properties we have, this comes to 1 KSI or 7 MPa. Very, very simple. 1 KSI dV dV cotangent theta. That's all you need. Again, one good benefit of using UHPC, if you don't use stirrups, you only check one section because the capacity is closest to the demand only in the end. And then they spread out after that. And if you don't have stirrups, then that's all you check. And that's all you detail, no stirrups. And very important that we insist on the tension time that's needed to make this system work. We tested a whole bunch of specimens in shear. WJA tested what we call coupon tests or component tests using I-beams that we designed specifically for the project. You can tell we have very large fillets, and we like that because we like the concrete to flow through. We also tested a whole bunch of products, including the FACA I-beam at NC State University and some building products, as you can see here. And in all cases, you will see a whole lot of cracks, and then finally one crack dominates. This is the FACA decked I-beam. They labeled one end as Econstruct. That's the company, my company name. That's the end that has no stirrups. The other one has stirrups, I believe, as per Ontario Ministry of Transport requirements. So the one that had the one that had, I'm sorry, go ahead, Philip. The one that had, go ahead.
No, it's not me. Somebody else.
Okay, the one that had stirrups, yes, did give high capacity, relatively high capacity. But at near ultimate, there were vertical cracks that reflected the locations of the stirrups. So the stirrups disrupted the flow of traffic, the flow of fibers. And if we have no stirrups, we still have very high capacity. So I don't know if there is a justification for putting the stirrups. I would rather make the web wider and get rid of the stirrups than make the web narrower and impose putting stirrups there. This picture still gives you the experimental capacity versus the theoretical capacity, and in all cases, we are quite a bit higher. Actually, we have a very large margin of safety in addition to the load factors. We also tackled pre-stress loss, interface shear, punching shear, corbels and ledges, end zone bursting stresses, and reinforcement creep and shrinkage, camber, and deflection. This gives you an idea about an inverted T that's very popular in buildings and how it can be converted to UHPC. Very amazing, very interesting. And we did full-scale testing, and we're very confident in our recommendations. And that's all in the report. For applications, obviously, a lot of people would love to see architectural UHPC, and that's moving forward. Again, coming back, decked I-beam, I am sold on that. Either the decked I-beam or the box slab are very, very efficient products to use. We're also doing sheet piling under contract with Florida DOT. This is supposed to be 1 foot, 12-inch, 250 millimeter solid sheet pile. We're changing it to a U-shape. We published in Aspire magazine an idea of converting the popular Next beam for Northeast Extreme T to a much more efficient UHPC, again, with zero reinforcement except confinement at the end and bars in the transverse direction. This product is also excellent, and it's good for shallow structural depths. If you're replacing a 4-span steel bridge with a 2-span overpass, same depth, you can do this and get away with it. We're also working on curved bridges, and in the PCI journal, in the March-April issue of the PCI journal, look for a paper on that represents a concept using UHPC for curved bridges. Piling, it could be an I shape, it could be an octagonal shape with a void inside, formed with the cardboard. Voided slab for residential construction, you can span 20 meters, 60 feet easily, 70 feet, no supports. Excellent if you have parking underneath. This project is ongoing, production is on the way, and we converted a steel framing system at the top with a column in the middle, 36-foot span. I'm sorry, I said feet again. We converted that to a clear span, 72 feet, with voids in the beam. So you can pass utilities, you can create all kinds of options. So That's what we did. We replaced all this steel framing with hollow core sitting on a box beam. And that's how the box beam looks. Saved quite a bit of materials. These beams are in production at this time. It's a 9-story building. Another example that I'll give real quick. I don't know about Toronto, but I'm sure there are parts of Canada, because I know I designed some of them back in the 70s when I was in Calgary. You have condos, wood condos sitting on concrete podium floors. But at that time, I used post-tensioning. Here, we're using precast, but you could tell it's very messy. There's a column in the middle, so cars that go in underneath would have to navigate through these columns. There's hollow core, there's rectangular beams where you have load-bearing walls. There's inverted T-beam. So it is quite involved. And this is the floor where you do the parking. And these are the products: rectangular beams, hollow core with stopping, rectangular beam when you have heavy load, otherwise it's hollow core, cheaper. And then the inverted T supports hollow core on one side and rectangular beam on the other side. We managed to change all of that with only one product that spans end to end. And the product looks like this. You have a UHPC U-beam, and you have conventional concrete deck on top of it. So the UHPC is only limited to the U-beam. That's all we need. Very shallow, very attractive, and it clears spans. So we changed from 105 pieces to only 14 pieces. So that's where you get the possibility. Imagine the possibility, 14 pieces, you actually save money. Of course, everybody loves architectural applications. So our sister company in Dubai is very active with architectural UHPC for cladding. And it's one of their projects. Obviously, is another one in the United Arab Emirates. There's a lot. And I know that there are some projects in Canada that are quite attractive. I believe the library in Calgary is a very attractive project. So can we wait? Should we wait until these turkeys make up their minds as to which design method? Please, no, don't. You already have enough information to do your design and to do it efficiently. The time is now. Don't wait. And this is my presentation.
Okay, thank you, Professor Tedros. And so, any questions? I guess now with the steel prices skyrocketing, I think definitely UHPC is like a more competitor in terms of cost. Do you guys think that could be the best time to use this material?
It's we have done. Actually, we're using it. We in our company we have several projects with UHPC. We're not waiting for codes or anything else. We're using engineer, and I'm going to challenge everybody that's listening to me. When the first cable stayed bridge was designed, was there a code for it? Structural engineers are innovative. They use their principles, their first principles, to do their design. They use their seal and their signature to guarantee this design, and it gets built. That's how innovations take place. The codes come later on, after things get established, and then you codify it. So in terms of cost, we figured that if you drop the cost of pre-bagged material, of course it varies from one place to another, from $2,000 to $3,000 a cubic yard. It's a little more than that, like $3,000 to $4,000 a cubic meter. That's a proprietary pre-bagged material. If you drop that to $1,000 per cubic meter, that's only 1/3 of the cost of what comes to you from a pre-bagged material with a secret recipe in it. And if you take conventional design, but it has to be the whole system, and convert it to a UHPC system and save 50% of the materials, when you combine these two together, you get a somewhat competitive product system, even on a first cost basis. But if you use a very expensive material and you don't optimize the structure, it will always be a lot more expensive.
Okay. Wendy Deng from MTO have questions. Wendy, do you want to raise your question to Professor Tedrow?
Yes, I'd like to know if it is feasible currently in Canada, so we can have this product fabricated.
I think, as I said, I don't know how many precasters you have in Ontario that are as prepared and as progressive as FACA. But even with one contractor who happens to also be a precaster, you already have what you need. You can implement it in Canada immediately if you want to. Somebody has to lead the way.
Yeah, I'd like to know, because we have some new structures over Highway 401. I think it's considered as a durability. It's as a benefit.
So we are waiting MTO first to implement these things, and then we follow.
That's true.
And the durability is definitely a plus. It's a big plus. But you notice that I didn't talk about it. It's a given. It's a given. So there's nothing to talk about. As I said, I strongly encourage you. I know structural engineers are very conservative. I'm willing to help on the first project. You just identify a bridge, and I will help you create a system that will be cost competitive with conventional concrete at no charge. And I'll send it to you, and you can take it and develop it further with help.
Yeah, when we selecting or screen the alternatives, maybe we can consider as one of our alternative.
Absolutely.
We like to consult you at the time.
Yeah, absolutely. I mean, we are doing a decked I-beam in Nebraska for the Nebraska DOT, and they're moving forward. We're doing the design, we purchased the forms, and it's all set to go. And so we're moving forward with it. As I said, it's, I mean, the very first project, again, luckily for you, in my opinion, you have FACA. And I'm not saying that because Philip is in the audience. I'm saying that because I know how resistant precasters are. I know that for a fact. You don't have that resistance. So all you need to do is find an overpass, two-span overpass, using your standard I-beam with a cast-in-place deck, and let's figure out how to convert it to. You'll be surprised.
Okay. So better get more project samples, if possible.
I'm sorry?
If possible, I like to get more project samples.
Yeah. I had a lot of projects. I was told, and I feel guilty, I was told that I needed to limit my presentation to 30 minutes.
Yeah.
And I think I exceeded my time. I have all kinds of examples that have already been implemented. So there's no problem.
Have your contact, email contact?
As I indicated, the best approach is to take an overpass with a 30-meter span. Be simple and conservative with that. Two 30-meter span, 20-meter wide or whatever it is. Do your conventional framing and allow me to propose a UHPC framing for it. Start with that.
Okay. Yeah. Thank you.
You're welcome.
Okay. Ying Li have a question and for Professor Tedrow. And is this environmental friendly and lower carbon emissions?
very environmental friendly, according to Dr. Vu and Dr. Foster. He can show that you're saving carbon dioxide, your potential. So all of these environmental measures are very favorable, more than conventional concrete and more than structural steel. Again, I didn't have that slide from their research, but it is available and we can get it. Philip can get it for you.
Okay. Here is the comments say FACAS Ontario is only certified by MTO to fabricate bridge span up to 17 meters, according to CPCI.
Okay.
Yeah,
Okay.
that's correct, because that's the limitation of our stressing bed.
Okay.
But you know, it depends. You know, like if you want to have a longer span, I mean, that's not an issue. We could make that happen. But the thing is that it's always, you know, the owners is always saying, oh, you know, you got to have the projects before we do an expansion. I mean, the only thing is just to get the PCI folks, CPCI folks, to come in and certify our plan. And that at the next presentation, which I was going to do, that's why we, you know, when we switched from normal concrete to UHPC, we need the CPCI to come in to see the whole process. Yeah.
Okay, Professor Yang Ken raise your hand, and Ken, do you want to questions?
Yeah, thanks, Hangang. So first of all, thank you so much, Dr. Tedros, for your informative presentation. I enjoyed it a lot. So I have a question regarding the deck type beam. So it seems that UHPC can make a very thin deck. So I just wonder, would it be difficult to create the longitudinal joints? Like, see, I guess my question is how it could be effectively connected to the adjacent deck type beam?
That's a very, very good question. Thank you for the question.
Thank you.
We are proposing a total UHPC superstructure. So the decked I-beam would have another decked I-beam sitting next to it with a gap that's about 300 millimeters or even 250 millimeters. Because the UHPC joint, again, has very, very high bond capacity to the bars, and you don't need to extend the bar a lot more as you would do with conventional concrete joints. And I don't know how you feel about it, but we are planning in Nebraska to have 3 inches of asphalt overlay. Some states and some provinces don't like to have asphalt put on concrete. If you don't, then you would do some milling and some protection and use it as your driving surface. But you're asking about the joint, and the joint, you have bars coming out of the flange, bottom and top, and they are overlapped in the joint between the 2 flanges. And it gives you a continuous superstructure in a transverse direction. We've already tested for that.
I can make a comment for Professor Tedros' explanations on Gardiner Expressway, City of Toronto. We just did the ABC constructions, and our joints, longitudinal joints, is about 220 wide. The lap bar, because we have a transverse reinforcing steel, is 150 to 180, and we have no problem. I mean, we finished about like a 10 kilometer those longitudinal joints in last year and the year before, which is all UHPC joints, which is performed very well.
Yeah, thank you, Dr. Tedros, for your answer, and thanks, Hangang, for your follow-up.
You're most welcome. I would also add to it that the bridge we are designing for the Nebraska DOT is a 3-span continuous bridge. So we have a joint over the pier between the spans, and we have longitudinal joint.
Okay, I guess now we have enough questions, and I guess I would like. Oh, we have one more, and Wahid.
Yes, Nahid. Hi. Thank you.
Well,
yes, thank you for the nice presentation. I have one more question following this question. If we use regular concrete for the slab, and we pour the joint with UHPC, now the UHPC element has a huge tension resistance comparing to regular concrete. So that tension might. I'm wondering if that tension can cause some fracture in our regular deck. I'm talking about, like, my main question is about those precast inverted T-beam systems.
yes.
Yes, when we put the joint with UHPC, now yes, that yes, you got the question, I think. Can you please? Like,
I understood the question. Wahid, I would strongly discourage you from doing that because I know Toronto gets cold and gets snow and gets de-icing chemicals, and the deck deteriorates a lot faster than any other component of the bridge. So it doesn't make any sense to use UHPC under the deck. I call it the carpet. Yeah, the carpet is what you need to preserve. So I would strongly recommend that you consider UHPC for the deck more so than the beam. And you're right, if you have dissimilar materials, you will get distress in the weaker material. So I agree with you, but it shouldn't be done.
Okay, great. Thank you. Thank you for the answer.
You're welcome.
Okay, I guess we are exactly on time. I would like to thank Dr. Terros and for these excellent presentations. And I think, in here in the audience, we have people from clients like MTO, City of Toronto, and definitely, that we will consider those girders and UHPC in our structures. Okay, thank you, Professor Terros.
Happy to help anytime. As I said before we started the meeting, I'm a Canadian.
Yeah.
So you guys need to consider me one of you.
Definitely from Calgary and colder than Toronto. Okay. Our next presentation will be Philip Lowe. Philip has 30 years structural design experience in building and bridges, and he is the design build project lead for FACA Incorporated. And Philip also responsible for the development of Darrow UHPC and ECC products in structural applications. Philip, that's all yours now.
Thank you. You can see my screen?
Yeah.
Okay, good. Thank you very much for this opportunity. Yeah, just, Dr. Terros has mentioned the company name for quite a bit, and just give everybody a perspective. When we first met him, we talked about this deck I-beam. It was actually in Cleveland, and that was Dr. Terros many years ago, and maybe 6 years ago, I think 5 or 6 years ago. And we were actually at a coffee time, and he wrote on a piece of napkin of what his idea was, and that's where we took it, and then developed it and actually fabricated the beam. So perhaps in the future I will share this our deck I-beam testing with you in more detail. But today we talk about UHPC H-Pulse and at the Lily River Detour Bridge in Highway 11, Kapuskasing, near Kapuskasing, Ontario. Now, I just want to acknowledge a couple of the two other people from that helped me with this presentation, and that's Don Guadagno, that's my boss, the president of FACA, and then Ima Buya, he's out of University of Windsor. Okay, now how do I move that slide? Okay, it moves. So presentation outline, some introduction of our product, and then the project background and the change proposal, UHPC power design, all that. Okay, so as a way of introduction, FAGA is a family-owned construction company. It was located in Roscommon, Ontario. Not what Dr. Tedros said in Toronto. It's near Windsor, Ontario. Has been in the business for the last 60 years, specializing in heavy civil construction. It has been, mostly in the transportation structures like bridges, that kind of stuff, and marine structures. Now we are getting into it, and environmental structures. Man, what happened? It doesn't want to move, right? Okay, so the Dura UHPC that we have is we formed a joint venture with Dura Malaysia to form Dura Concrete Canada, and then this is a proven UHPC product. It has been used in many MTO contracts, and it meet CSA, MTO, and as you can see in the previous presentation, the PCI standards. So we are precast facility, CPCI certified, and we use local Canadian and Ontario raw material as much as possible. So the material properties for Dura, this is the CSA standard A23.119, the material identity card. You can see for the compressive strain is here, like the mean that we tested around 140 MPa, and the characteristic is around 130, and that's the category 120, and then all the tensile strain characteristics are here. Then for durability, as we mentioned, this is a very durable product, and some of the more important parameters that we're used to is the RCP, chloride ion penetration is like, we tested is generally around 34 coulombs, which is less than 100 coulombs. So those are very, very good numbers. Oops. So we did some testing last year for MTO for the DSM pre-qualification. Here is the mock-up sample casting. This is to simulate a closure joint between precast elements, and with MTO here to witness the casting in our yard with this mock-up sample at a 2% slope. And then when 7 days later, they came back and we did a coring through the joint. So there's a core. This is UHPC, and there's normal concrete. And the bond is just about perfect. And we saw cut through the joint, and you can see again, the bond is really good. Okay. MTO has also asked us to require a whole bunch of other tests that we have to do. So for DSM, they have different parameters here, like the 28-day has to be 130 minimum instead of 120 according to CSA. So it's we ended up with 150, and they don't use characteristic strength, more on the average. And then the tensile strength, again the RCP, the MTO only require less than 300, but we have very low numbers, 27. And there's a linear shrinkage, freeze-thaw, 300 cycles is still 100%, so no change. So these are just material properties. Now we talk about the project. The Lily River Bridge carries 2 lanes of the Highway 11, which is part of the Trans-Canada Highway. The project is to replace the existing single-span bridge at the same location, and so the consultant Stantec has required a detour bridge. So the next slide here shows the detour bridge, which is some distance from the existing bridge here. So this is to Kapuskasing and there's to Moonbeam, and this single lane detour bridge is controlled by temporary signals. It's it's one of those Bailey bridge. Okay. So for the foundation plans, we have the east abutment, west abutment. The design was 6 steel H-piles for each abutment. So one of the abutments, which is the west abutment, we have a change proposal to change to replace the H-piles, the steel H-piles to UHPC piles, and then we also maintain the batter. So we know that UHPC piles probably require less than 6 piles. So, but we decided to just keep the same number of piles and keep the batter as well. So this is the foundation design. The borehole logs here showing bedrock at around 13 meters below, 12 meters to 13 meters below grade. So 13 meter is where the east abutment is, and 12 meter is the west abutment, which we are more interested in. It shows cobbles and borders, so we have to fit the piles with pile driving shoes. So based on the IFC drawings, they said the pile had to be fitted with driving shoes. We didn't change that. Estimated pile length is 13.8 and 13.5 meters. So that's why our stressing bed is just perfect. It was 15 meters, so we cast 15 meters pile to make sure that it actually can go to the bedrock. And these are the serviceability limit states, axial resistance required per pile, and the ultimate limit states. So this is the UHPC piles cross sections that we have proposed. It's a pre-stressed, pre-cast UHPC piles. It's a 300 by 300 H piles, more or less, and with 10 of these pre-stressing strands. All right. So the UHPC H pile design is we had Dr. Sri Taran from Iowa State University and Dr. Cam Eng from Wyoming University, because they have done a few of these pile design for the Iowa DOT, and they have actually used it on a couple of bridges. So we get their expertise on this one here. So they design based on the CSA S6. They require 100 MPa at the time of transfer, which is high, but that's what was required. So 150 MPa during service. Then the design load is the same as jacking stress is this, and they did. Dr. Eng is a geotechnical engineer, and he did all the WIP analysis for us for the power drivability, and then it concluded that we need a geotechnical axial resistance of 900 kilonewtons, which is 2 times the ultimate limit states. So we did some environmental impact. Somebody asked just now was about the low carbon emission. Yes, we did the comparison between steel and UHPC piles. If you look at the mass let's say 100 is the benchmark for steel power or the blues. Okay, so the UHPC power is around 18% more weight because it's concrete, but the embodied energy to produce steel powers versus UHPC powers, you see a drastic decrease from 100% to 25. So that's like a 75% reduction. Geez, I don't know what happened here tonight. The carbon dioxide emission, again, very good, reduced by almost 70%. So is the global warming potential. So UHPC power has definitely the environmental benefits. So here are some pictures of the fabrication in progress. The casting of the UHPC powers. It was witnessed by CPCI, like I say, MTO staff from the Mirror office, and also from and then the CS staff. So they were all there, and including sampling of the QA specimens. So it is a 15-meter long precast pre-stressed UHPC powers fitted with power driving shoes. So doing some QA QC testing here, and QA obviously is somebody, a lab that is determined by MTO, and then we have our own lab from Wood, which is also MTO qualified labs. So it gives you we did this comparison here, like a 4-day moist cure, 28 days, and then we have this steam curing, because that's what the designer require, that we had to have 150 MPa, and if it is just a lab cure, we're not quite at 150, but when we add the steam, we did the steam cure 90 degrees centigrade for 2 days, then it increased the strength. And then we did the 4-point bending test. Those very good. MTO requirements 15. We have exceeded all that. The RCP, again, MTO required 300. We are all less than 100. And we also did some test powers just behind our yard there, and we use the foundation investigation information from a nearby bridge, the French Line underpass, which is the exit 40 at Highway 401, which is near our yard. We use that, and then we had our geotechnical consultant come out and do all the PDA, all that stuff, and just to make sure that this works. And we drive it vertically and at the batter, and they give us a set criteria to be used at the Lily River Bridge. So then we start the construction, and we drive the powers. Because for some, we were told that the powers would be like 13.8 meter to bedrock, but because the concrete section has so much friction resistance that it didn't really reach that much. So our 15-meter power, we still have like quite a bit of power sticking up here, because we only drove it 6-7 meters, 7 to 8 meters for most of them. So we cut off the powers and cast the power cap, all that. So the PDA results during construction, we had the CA consultant that did all the PDA, and then the power was set at 8 to 9 meters below existing ground. So so we have a 15-meter powers. So some of them was like 7 meters sticking out, but for comparison, the steel edge powers was 13 meters below ground. So UHPC powers is there is a benefit here. And then after a year of service, the D12 bridge is removed, and we decided to extract some of the piles to see what is going on there. And we managed to extract 2 of the piles out of the 6. This pile here, actually, the pile, we have 6 piles, and we have 3 different types of pile driving shoes. And so one of the shoes didn't work that well. It dislodged, right, during the driving process. But the remainder of the piles are in good shape. This pile here, pile number 3, the driving shoe is still good, and none of the piles is damaged. So the other 4 piles, we tried very hard to try to extract it, but they didn't want to budge. So they are always in the ground now. So what are the lessons learned here? Conclusions. UHPC piles can be driven with conventional pile driving equipment. UHPC pile is slightly heavier, but can be handled by conventional transportation equipment and hoisting equipment. They can be tested the same way as steel piles. And UHPC pile, as you can see just now, has higher capacity. So basically, we need shorter steel UHPC piles than steel piles in this instance. And obviously, UHPC piles are more environmental friendly. So we are going to do more research, and University of Windsor, we are going to be trying to do some combined pile, axial and bending, such as piles for integral abutments, pile splicing. Because like I said, we are limited to 15 meters. If we want to do a 30-meter piles, then we may need a pile splicing. So we need to test some of that. And then we want to look at friction and versus end-bearing piles. There are other studies that we are supporting, which is the Alabama University is a PCI sponsor, pile studies. Also a UHPC consortium, which is the Iowa State University, has a pool fund study, which I think is driven by Iowa DOT. So we are supporting part of that study too. Acknowledgements. Some of the UHPC pile formwork is actually from a funding by NSERT, and so we want to acknowledge that. And of course, MTO for approving our change proposal, and the designers and the faculty team. That's all I have. Thank you.
Any question for Phillips?
Sorry, my equipment didn't work very well today.
No, you're very good. MTO have any question for Phillips?
Good presentation. So good to know the UHPC piles. So we have the option. We have the option in the future, not only HP piles, steel piles.
Well, now steel prices are so high, and probably
yeah.
Now the concrete probably will replace steel.
Yes.
Yeah, it has been used before, so
Yeah. Very good. Thank you.
I guess the other government agency and the rated MTO, I mean, take the leading role, and so provide us some guidelines, so we can use those new materials.
Yeah, if we have the new structures to be built and the design, we can consider some innovations.
Well, but you always can update your structure manual, all these things, and and OPS, and so we have some standard specification, standard guidelines, and so like like MTO have all the technical expertise and most.
Yeah, we need to start with some new structures to use the new technique. Okay, thank you.
May I have a question?
Yeah, go ahead.
Oh, yeah. I just want, so first of all, thank you for the presentation. And I have a question for this kind of the pile, is separated with the different bearing load. One is the use the friction, or another one is use the ending bearing capacity. So I just wonder, for this kind of pile, I have get more information about is the two kind of the capacity. One is from the friction, another one is from the ending bearing capacity.
This is a good question. I mean, I'm not the geotechnical expert, but this is something that they always, they did the drivability analysis for me, and the intention here at Lily River Detour Bridge is actually an end bearing pile. That's why we designed it to. We built it. I mean, fabricated the piles long enough to go down to the bedrock, but it only go down 8 to 9 meters and then it stops. So that tells me, it's actually it be having more like a friction piles. So that's why we need more study research. That's what those guys at the Alabama University. They want to look at different soil profile, soil types. And then they try to determine what kind of piles is going to be. But most of the piles I understand are friction piles anyway. So, all right.
Friction plus the tip, I think.
Say that again.
Philip, in Canada, our practice, we also use end bearing pile. I mean, because the friction is not the friction is not reliable.
Yeah.
And second, because when we dry the pile, which is we have a so-called Haley formula.
Yeah.
Which is basically that's how you control how deep the pile will go and end the pile. Basically, that's if you look at the geotechnical report, basically like 99.9% like end bearing piles.
Yeah, you're right. I mean, the thing is that we see mostly end bearing piles here in Canada. I know that, and there are some areas along the 401. I think we also see quite a few projects that were designed using the friction piles. Okay, so.
Okay. Any more questions for Phillips?
I'm just thinking the advantage for this concrete piles is compared with the HP piles, maybe the lateral friction or lateral resistance is higher, should be, because these HP piles look so flexible. If it is in the very soft soils, I don't think HP piles has the advantage compared with this concrete pile.
Yeah.
Okay. If no more question, then we'll go to next presenter, which is Dr. Ken Yan. So Yan, a rising star in our field, and Professor Yang she's assistant professor at the Department of Civil Engineering and McMaster University. she see her PhD from University of Buffalo and State University of New York. And I think that's one of the seismic research center in the United States. Okay. And a long time ago, we know that we even make joking. I mean, supposed in California, but somehow in New York State, supposed no earthquakes. They have like a seismic research center in there. And research basically on resistance of reinforced and distressed concrete, highway bridges from surge to extreme events. Okay, so we are out for the deal, and now it's all use Professor Yang. Go ahead, share your screens.
Yeah, thank you, Henggang, for your introduction. I like to put my presentation in a presentation mode. Okay, here you go. Okay, good evening, everyone. And thanks to Dr. Tedros and Philip for the comprehensive presentation on UHPC. So my presentation would be on a smaller area, which is the seismic application of UHPC. So yeah, my name is Ken Yang, and I'm currently working at McMaster as an assistant professor. So today I'm going to talk about our research efforts on using an ultra-high performance concrete to reduce earthquake-induced damage to precast concrete piers and to achieve seismic resiliency. So I would like to start this presentation by illustrating why we need to facilitate the implementation of accelerated bridge construction, which we call ABC, in seismic regions. So we know Canada has over 74,000 bridges, and about half of them are over 50 years old. So as you can see here on this slide, the 2019 Canada Infrastructure Report Card, it makes it very clear that the rapid aging of Canada's bridges is alarming. So as you can see here, as of 2019, the percentage of Canadian bridges that are in poor or very poor condition has tripled since 2016 to around 12%. So these bridges, of course, they need repair or replacement within the next 5 or to 10 years. So the bridge condition is actually not better in the United States. So each year, the American Road and Transportation Builders Association puts out their annual bridge report. So this report highlights the general condition of America's bridges. So in general, about 7.3 of Americans' bridges that are rated as structurally deficient in 2021. So in other words, that means every 1 in 3 United States bridges needs repair or replacement. So this is a problem not only in Canada, but also in other states. So we know there are numerous daily crossings on these structurally deficient bridges. So, repairing or replacing these deteriorating bridges will cause significant traffic disruptions, mainly due to lane or road closures. So that's why we say that need for the adoption of ABC is greater than ever. So compared to conventional construction, ABC offers tremendous savings in construction time, which can effectively reduce the transportation delays. Also, by limiting the on-site construction activities, ABC will improve the work zone safety. So that can be beneficial for construction budget control and also minimize the environmental impact. Absolutely, we can say that ABC is a more time efficient and sustainable construction method. So PBES, which is prefabricated bridge elements and systems, they have been recognized as an important technology of ABC. However, their application is limited in moderate to high seismic regions. So to facilitate the utilization of ABC in seismic regions, so research needs to be done to adjust the seismic limitations of existing precast concrete systems. So here I classify or characterize the precast concrete bridge pier systems into two types. And the first one is emulative pier. So emulative means that it's emulative of cast-in-place construction. So to resemble monolithic concrete behavior, we use special connectors, such like the grouted duct connection, mechanical bar splices, or member or socket connection. So we know it can achieve very similar behavior just like a monolithic pier, but the problem is that it will develop permanent damage or residual displacement after an earthquake event. And also the connection has to be carefully designed, otherwise the ductility will be a big concern. And so non-emulative pier system, so it's kind of on the contrary side. So they are typically accompanied by the post-tensioning strand, unbounded post-tensioning strand. So post-tensioning can provide a restoring force to bring the system back to its original state after the removal of earthquake loading. So we know the nonlinear elasticity is provided by joint opening. And also, we know through developing this rocking behavior, the non-emulative system can reduce the residual displacement and also minimize overall damage. But even though we know that this non-emulative pier system can alleviate tension-induced damage, however, the rocking or the gap opening will induce significant compression-induced damage at the rocking toe area. So our research seeks to address this limitation. Specifically, we are trying to answer these following questions shown on this slide. So we know UHPC has high compressive strength and sustained post-cracking tensile strength. And so we want to see if UHPC can be a solution to mitigate concentrated concrete damage, which is a limitation in non-emulative precast concrete pier system or rocking concrete pier system. So here we designed and fabricated 3 large-scale precast concrete pier specimens, and this specimen is composed of a precast concrete cabin, 5 precast concrete column segments, and a precast concrete foundation. So they are connected with each other using unbounded post-tensioning strands. So the difference, or the 3 specimens have varying materials for the bottom segment. So here you can see in specimen 1, we call it reference specimen because everything is built with normal concrete, NC. And specimen 2, what we did is that we use UHPC to replace the normal concrete just for the bottom segment. And so what we further did to specimen 3 is that we remove all the mild steel reinforcement from the UHPC segment and see whether it can still behave satisfactorily under the simulated load. So all the 3 specimens, we put it under reversed cyclic displacement controlled loading. And here are the test results. So from these 3 pictures, you will see all the 3 specimens, they just behave like a rigid body rocking over the foundation, and gap opening mainly occur to the bottom joint. So because of this rocking behavior, they can develop very good self-centering, but the energy dissipation is limited, but that's what we expect because the only source for energy dissipation in this system is the post-tensioning strand yielding. So what we can see here by comparison is that UHPC can develop higher stiffness and higher strength no matter or whether or not you use mild steel reinforcement in it. So, and basically UHPC specimen with rebar or with rebar and without rebar, they show very similar behavior. So then from that, we can see UHPC really has the potential of keeping excellent seismic performance without the use of mild steel reinforcement. So this is a good news because we can, from that, we can reduce the material and the labor related costs. So the UHPC's benefits can be further demonstrated by our numerical and analytical results. So from this slide, you can see our numerical model and analytical models. They can both achieve good agreement with the test results. So we are confident about in using it to further understand the UHPC's performance. So if we zoom in and have a close view of the bottom segment. So you will see that normal concrete has a large piece of concrete spot off, but UHPC with rebar and without rebar, they can both maintain the specimen in a good shape with minimum damage or minor damage. And this is because the UHPC they have a high modulus of elasticity and the compression strength, which can effectively reduce the principal compression strain. So with that, we can manage to control the concrete spalling in a very effective way. Okay, so that's about the non-emulative pier part. So for this phase of study, we rely on the enhanced mechanical properties of UHPC to mitigate the earthquake-induced damage to precast concrete piers. And at the beginning of my presentation, I think I mentioned that non-emulative pier, through developing rocking, it can achieve a good self-centering, and also it also performs very well in terms of the overall damage control. But the problem is that the concentrated concrete spalling and the energy dissipation is limited. And on the other hand, emulative pier can maintain the stiffness and the strength very similar to casting place pier or monolithic pier. But the problem is the damage would be excessive. So from here, we are thinking maybe we can approach this problem from another angle. So which is that we are trying to propose a new precast concrete pier system, which we call it hybrid pier. And so for this pier, we want to see whether it can combine the benefits of these two existing precast concrete pier systems. So here are the research goals that we set for the hybrid precast piers. So first of all, we want so this research was implemented in two phases, and the first one is that a configuration of the hybrid system was selected, and then we perform a two-tiered analysis on it to select important design parameters, and then we fabricate three hybrid pier specimens with the selected design parameters and test it under quasi-static cyclic lateral loading. So we also incorporate UHPC into the hybrid pier and see whether they can mitigate the damage types specific to hybrid precast piers. Okay, so from this conceptual drawing, you'll see the hybrid pier is composed of three precast concrete column segments, and they can be constructed with a precast foundation and a precast capping for rapid construction. And so the bottom segment is connected to the foundation by a socket type joint. So socket type joint is to emulate casting place connection. Of course, other emulative connections can be also considered. And so the upper two column segments and the capping are connected to the adjacent elements with non-emulative rocking joints. So we say it non-emulative because there is no mild steel reinforcement continuous across these rocking joints. So all the column segments, capping, and foundations, they are assembled using unbounded post-tensioning. So under lateral load, the bottom segment, which is a yellow one, so it is expected to bend like a monolithic column, so it's therefore referred to as bending segment. And the upper column segments are expected to rock over the bottom segment, so we call it rocking segment. So here I think there are several important parameters we have to design to achieve the design objectives. So the first design objective we want to achieve is that we want the stiffness and strength to be comparable to the ones of the emulative pier or the casting place pier. The second one is that we want the bending and rocking response. We want to develop a balanced bending and the rocking response. So, and the third one is related to damage control, which is we want to see whether we can delay the mild steel reinforcement yielding and also the post-tension loss. So a big challenge for designing these hybrid piers is that all these design parameters are not independent from each other. So here we identify or established a series of design steps to systematically identify the optimal design variables. So the first step is to establish reliable methodologies to characterize the response of the non-emulative system and emulative system separately. And then we want to conduct the preliminary design to determine a viable range for variables in the hybrid pair. And once a viable range of the design variables are determined, we use the analytical model to capture the interaction between the non-emulative and emulative responses and to determine a suitable values for all the design variables for given performance matrix. So for characterizing the response for the non-emulative system, we use the analytical model based on a monolithic beam analogy with the equivalent plastic hinge length. So here you can see the predicted pushover curve and also post-tension force response were all in good agreement with the ones obtained from the test. So the rocking stage stiffness was predicted reasonably well, but the initial, which is a pre-rocking stage stiffness, was overestimated a little bit, and so we think it's likely due to the imperfection of the contact surface between the precast concrete elements. So then we used the same geometry and same cross-sectional details to study an emulative system. So basically we did a moment curvature analysis, and then we convert the moment curvature curve to a force displacement relationship at the global level. So in terms of the post-tension strength behavior, we use the displacement compatibility to capture the change in the post-tension force due to the bending deformation. So here, because we don't have the experimental data for emulative system, so we use finite element analysis results to check the accuracy of the analytical model, and then we found it can predict the response reasonably well. So with the validated model, we can proceed to the preliminary design. So we worked on the relationship between the moment at the emulative and non-emulative joint. And the purpose is to ensure both rocking and bending can take place under seismic load. So to achieve this, we set up a relationship or set up a design rule, which is the proportionate moment at the non-emulative joint should be somewhere between the moment needed to initiate the gap opening and also smaller than the ultimate rocking moment. Here, this slide summarizes the range of the height ratio and the determined for each initial post-tension force level and reinforcement layout. And with that, we can move forward to our next step of the design. So the problem is that the preliminary design or the method that we used previously, it cannot consider the interaction between rocking and bending, but rocking and bending in this system, they are interdependent because both the flexural deformation and the gap opening at the rocking base, they both will cause elongation or shortening of the post-tension strands. So then here what we did is to establish an analytical model to capture that interdependency. So this analytical procedure starts by setting a value for the extreme compression fiber strain at the bending base, and then we just do the equilibrium of the forces at the bending base to find the location of the neutral axis. So then we can easily calculate the bending moment at the bending base, and so then we know the moment is proportional to the height, so we can easily find the moment at the rocking base MR. But because the post-tension force changes due to rocking, so that will make the section equilibrium at the bending base no longer exist. So then we have to do the we have to recalculate the neutral axis steps at the bending base through iteration until the section equilibrium can be satisfied at both the bending base and the rocking base, so we can output the performance matrix that we need. So it's like the lateral force, bending displacement, and the rocking displacement. So here we use this analytical model to investigate the effect of different design variables on different performance matrix. And the first performance matrix what we're looking at here is the force versus displacement relationship. So here what we found is the hybrid system with the longitudinal reinforcement ratio of 2.2% and the height ratio of 0.5 had a smaller stiffness and strength than the other peers. And this is likely due to the higher longitudinal reinforcement ratios and the lower height ratios. Both of them will result in a smaller bending deformation. So then we remove these things, these candidates from our selection pool. And so the next slide is about I want to study how these design parameters will affect the balance between bending and rocking. So here we use a indicator which is called bending contribution ratio to serve as an indicator of the bending and the rocking balance. So the bending contribution ratio is defined as a ratio of the drift at the top of the bending column segment over the total drift at the mid-height of the capping. So basically, larger values of the bending contribution ratio indicate that more displacement is caused by bending as opposed to rocking. So here, we know bending can provide energy dissipation to the hybrid system, while rocking can enable self-centering. So what we found here from this parametric study is that the bending contribution ratio decreases with the increase in height ratio, and also it will decrease as an increase of the longitudinal reinforcement ratio. And the impact of the initial post-tension force is more pronounced at smaller displacement than larger displacement. And also the third one that we're investigating here is the effect of the design variables on the damage controllability. So through rocking, we know the hybrid system can delay the longitudinal rebar yielding, and the delay in rebar yielding in the hybrid system was less significant for higher initial post-tension forces. That's what we found here. So then finally, we said that we were going to select the bending height ratio of 0.5 to 0.6 and initial post-tension force of 20 kips to 30 kips per strand because they can lead to a delay in mild steel reinforcement yielding. So I talk a lot about the design methodology, but here is how UHPC come into place in this system. So UHPC, here we use UHPC for the bending segment for this hybrid pier system to improve their seismic performance, mainly because we think that will reduce the concrete spalling, and also we can develop a well-distributed narrow cracking. And so also we want to see whether it can enhance the resistance against the prying action within the foundation. So here a UHPC mix was selected so that the replacement of normal concrete by UHPC can improve the damage control, but at the same time we want to ensure it will not compromise the balance between bending and rocking. So the UHPC mixes that are considered here, they are all commercially available, and they are called Ductile, provided by Lafarge Holcim. So here 6 different mixes were considered, and they utilized 2 different types of premixes and 2 fiber types and 3 fiber volume ratios. For each of them, we did a uniaxial compression test, uniaxial tension test, and 3-point bending test to characterize their material properties. So here I would like to show how they perform under third bending test. So from here, you'll see that unlike normal concrete or the UHPC mixes, they can maintain integrity. And so this is on to the UHPC's higher tensile toughness. However, the bending contribution ratio could decrease as an increase in UHPC's toughness. So then finally, what we found is that UHPC mix 1 and mix 5, they were capable of maintaining the balance between bending and rocking. And so more specifically, that means we want to keep the average bending contribution ratio of about 50%. And so our final selection was given to mix 1 because mix 1 had higher compression and tensile toughness than UHPC mix 5. And so that basically shows that mix 1 has greater ability for damage mitigation in the hybrid system. So this is the finally selected design variables, including initial post-tension force, longitudinal reinforcement ratio, bending to total height ratio, and also the UHPC type to be used in a bending segment. So then we are able to move to the experimental demonstration part. So here is the first specimen that we tested for demonstrating the hybrid pure precast pure systems performance. So here in this picture, you will see the bending segment. The first specimen is made of normal concrete. So it was inserted into the steel bracket fixture. And the steel brackets attached to the steel brackets are attached to the strong floor, and they were designed to remain elastic throughout the whole testing. And the two steel brackets were post-tensioned to each other using 6 horizontal threaded rods, just to create contact between the pier and the bracket. So we also put 2 steel tubes underneath the pier just to provide a bearing surface under the pier, and also to create some room for the strand anchorage chocks underneath the pier. So here we did 2 sets of quasi-static cyclic tests. The test phase 1, we focus on investigating the damage occurring near the long emulative joint, and test phase 2 focused on investigating the damage occurring at the emulative joint. So here is the results. I should be able to play this video. So you will see the lateral displacement can be treated as a combination of the displacement due to rocking and bending. So the large area enclosed by the force bending displacement hysteretic loop indicates that the energy dissipation is achieved and is mostly due to bending. And the rocking response shows good self-centering, but there are 2 apparent concrete damage near the top of the bending segment. So that's the concrete cracking and the crushing close to the long emulative joint. And then from here we can see that after the lateral displacement reached about 2%, 2.3% drift ratio, concrete spalling or cracking at the long emulative joint will result in a significant loss of the contact surface for rocking. So that will weaken the rocking response. So this is also why we observed the stagnation in strength at the global level. So in test phase 2, we pushed the pier to a further displacement, and also put the steel jacket on top of the bending segment to serve as a rocking joint protection. So here you will see the damage and after about 4% drift ratio, the damage shifted from the long emulative joint to the emulative joint, and the damage near the emulative joint included fracture-induced concrete cracking, spalling, as well as the shear damage in the column region inserted into the steel brackets. That is because of the prying action. So here, what we observed is that the concrete crushed within the steel bracket region when the lateral displacement reached 4.5% drift ratio, and that is because of the excessive shear cracking at this region. So, and this is also the reason why the lateral strength decreased fast beyond 4.5% drift ratio. And in specimen 2, we replaced the normal concrete in the bending segment with UHPC, and we also did 2 sets of quasi-static tests. And the first test, we didn't put the steel jacket on because we want to study the rocking-induced behavior. And the test phase 2, we put the jacket on to focus more on the emulative joint. So here, Let me play the video. So here, by using UHPC, we can see the first rocking induced cracking at the top of the bending segment. They occurred at a later time. So we observed that at about 2.3% drift ratio. And after we observed the cracking, it quickly propagated downwards. So compared to specimen 1, the spalling failure observed in the normal concrete bending segment near the rocking plane was definitely alleviated using UHPC. So because of this better performance or this better damage control ability, so the lateral strength consistently increased until the displacement reached about 3% drift ratio in the lactive direction. So after this displacement, the rocking-induced vertical cracking at the top of the bending segment, they propagated downwards, and that will reduce the resistance to rocking and reduce the strength and increase the rocking displacement. So again, we put the steel jacket on and push the displacement to a larger specimen to a larger displacement. So this one we see as an increase of lateral displacement, both rocking and bending response increased due to the existing damage at the long-emergent joint, and specimen had more severe rocking-induced damage at one side compared to the other side. This is because of the lack of symmetry in rocking and bending displacement. So in the last specimen, we had the UHPC again in the bending segment, but this time we put the steel jacket on top of the bending segment for both test phase 1 and test phase 2. So then we'll see that due to the confinement of the provided by the steel case or steel jacket, and the damage at the top of the bending segment was limited to just hairline cracking. So then the protection of the long-emergent joint from the damage enabled this specimen to develop a very stable balance between bending and rocking displacement. So the specimen had a very stable increase of lateral strength at all displacement magnitudes considered in test phase 1. And so then one more time we push the pier harder, and then specimen 3 didn't show any additional apparent damage at the long-emergent joint beyond test phase 1. I think that's because of, again, UHPCs are better mechanical properties. So here's what we also observed is that the lateral strength first dropped at 6.7% drift ratio, and that's due to the concrete shear cracking within the steel bracket. But this happened at a much larger displacement compared to normal concrete specimen. So that makes us to conclude that the damage at the emulative joint was successfully alleviated using UHPC. And then the benefit we gain from that is that a delayed lateral strength degradation. Okay, so just to wrap up my presentation, it's already 9. So for the long-relative pier, I think our researchers answered this question, and we demonstrate that concrete spalling can be prevented by using UHPC, either with or without mild steel reinforcement. And for the hybrid pier, and so we proposed an analytical model to conduct the design, and this model can be also used to select a UHPC mix to achieve the design objectives. And our experimental results also demonstrate that the feasibility of this new system to achieve a better seismic performance. Okay, yeah, thank you very much for your attention. And thank you also for taking time from your weekend to attend this webinar. And if you have any question, I'll be happy to answer.
Wow, it's very impressive research. And so, Wendy have questions. Is there a shear key set between the connection interface?
Yeah, it's very interesting study in the test. I like to see, is there any shear key set between the connection interface?
So Wendy, for both of them, there's none. So for example, this one, so they are just, hard contact between each column segment. So I think this picture will show better how they are connected. So there are the interface of the column segment. So you'll see the only connection is the unbounded post-tensioning strands, and there's nothing or no continuous milestone reinforcement there.
Oh, okay.
Yeah,
There's some share case like a female to male. I think it will be improve the performance. Might be.
Yes, it will. Yes, Wendy, you are right. It will. The reason that why we didn't include any share key in this test is because we actually, I didn't show in this presentation, but another part of our research is to intentionally make them to slide against each other. So we want to achieve some slide. We want to achieve the allergy dissipation. We want to dissipate the earthquake-induced allergy through their friction response. So that's why we want it. We even, as you can see here in this picture, so we even put some silicon at the interface to make them to make some slippage happen at the interface, so we can rely on their frictional response to dissipate the allergy.
Yeah, I think you testing this specimen is similar, is a mimic like some ramp structures for the elevated structure. They has the single like a hammer typed single column pier, but this type of pier in our Ontario, I think is less used to. But most of the time we use the twin column with the precast like a pier, right? Conventionally pier cap. Is that possibly you also can do some models with the twin column piers? Maybe it is a better for the practice compared with our true situations. And also from this testing, I think this is a free vibration, right, for the pier cap. And I just concluded that if it is the integral the pier with the superstructure, I think the seismic will be improved much, right? Yeah, from your test, because it is a free vibration on the top, if we integral with a superstructure for the single pairs, I think it will be improved much for the performance.
Yeah, when did it, and the test that we're doing, we did some free vibration tests, but the test that I showed in this presentation, they are displacement controlled tests. So that means we actually control the displacement at the top of the pier for the loading protocol that we specified, and then. But I want to answer your question about the integral connection with the superstructure. So I think our argument for this system is that it will reduce because as you can see, the stiffness is actually weakened compared to it's kind of a weakened structure. So then that will, under seismic loads, it will also reduce the demand for the superstructure. Otherwise, you will have a large moment transferred from the substructure to the superstructure. So then that will cause some damage to the superstructure. And also right now, this system haven't been studied at the whole bridge system level. So then we actually have little knowledge about how this will affect other bridge components' behavior.
Yeah, okay. Yeah, good start.
yeah, thank you, Wendy. I know.
Later.
Yeah.
Okay, there's another question from YL. The title is about seismic vigilance. How do you define the concept of vigilance by the performance indicators?
Okay, yeah. Are you trying to say something or? Okay, I can directly answer from that. Yeah, it's a good question. So I think there are different definitions for seismic resiliency, but here what we want to see is that by using UHPC, you can manage to control the damage to the system. So that will require very small amount of repairing after an earthquake happens. And another thing that we think this system is good for, or can achieve seismic resiliency, because everything is constructed separately. So if you have some damage at the bottom segment, you can just quickly replace the damaged segment with a new one. So that will significantly reduce the time needed for repairing or replacement. So I think seismic resiliency is definitely something related to how quickly you can recover the bridge's normal operation. So that's how. So this is what we can help with that perspective.
我做这个 poetry， 我要做这个 poetry 哦。
现在
Somebody,
我们现
Arthur,
在
can you mute your
不是现在做，
Arthur?
不是现在
Can you
做。
mute your... Okay.
Yeah, I hope
He
this
has a
answers your
question.
question.
Thank you, Dr. Yang. I think Young or Yang for the presentation. Sorry for the pronunciation. I have two questions. One is for the steel bracket. Can you please explain why did you use those steel brackets? Again, I didn't get that.
Okay. I mean, the second phase of study. Let me quickly go to that slide. Yeah, so the reason is that so we are expected to have rocking response developed by the upper segment and bending response developed by the bottom segment. So because of the rocking, it will induce the concentrated compression at the rocking toe area. So then that will induce some compression demand on the bending segment. So then we are trying to protect this connection from damage, so then it will provide a good contact for the rocking response. So that's why we think this steel bracket is necessary to.
Yes, that makes sense. What about the yellow one, yellow bracket?
Oh, yellow one. Oh, sorry,
Yes.
I thought you were talking about the upper one. Yeah, this one is to kind of clamp the column. Connect the column together. So the reason that we use this bracket is that we are not building an actual foundation just for the cost concern, and then we use the steel bracket to simulate the socket connection, which is a typical connection for precast concrete construction.
Yes, I got that. Okay, I'm thinking that might be the reason that the cracks are a little bit small, because you are putting a lot of compression on the hinge around hinge zone. Anyway, my next question was about your non-emulative piers.
Mm-hmm.
Because in Canada we don't have that much seismic demands. Do you think that can be a good option for Canada? Because I saw the hysteresis loops. They didn't provide that much energy dissipation.
So I think the precast concrete substructure is just not less often used as compared to the precast concrete superstructure. So then not only in Canada, I think worldwide that's the case. So we are trying to promote the use of precast concrete for substructure. Hopefully in the future we can build the whole bridge using precast concrete. So then that will accelerate the construction time. So that's the intention, that we focus on studying the precast concrete substructures. But I know in practice, it's not that often used right now. We typically just go with the casting place construction, but in casting place piers or substructure.
Yes, great. I agree. Thank you.
Thank you.
Okay, any more questions? So if no, I have an announcement to make it, and a German professor is coming to Toronto to do some pre-stress cable detections research and project in 2 weeks, include post-tensioning tendons and bridge girders and parking garage decks, and pre-stressing strengths in precast beams and double teams. So we will issue a post CSEA webinar again in 2 weeks, and hopefully everybody can join the next webinar. Okay, so I would like to make a final remarks, and first I would like to send thanks to all the 3 presenters, Professor Tedros, Philip, and Ken, Professor Yang, for excellent presentations for our associations. Take away from tonight's presentation, basically, as Professor Tedros said, it's the time now to use UHPC concrete in our practice. Okay, I know in GTA, Greater Toronto Area, and in next 10 years, and we probably have, I would say, like $50 billion capital projects. And if you guys watch news and City of Toronto just released the capital work project in next 10 years, $46 billion. If you're talking about the bridges and structures, that's probably $2 billion. And in Metrolink, we all know we have a big subway structures ongoing, which is Ontario Lines. And the first contract, Ontario Line, North Ontario Lines, is all elevator. It means it's all in elevated structures. And that could be definitely have a place for UHPC. And so now we rely on the consultants. And in this audience, we have consultants, we have owners, and basically, for us, City of Toronto, we don't have a technical capability. We rely on consultants to provide your recommendations, and also we rely on MTOs as the leading agency to update their standard menu and standard specifications, OPSS. So in our practice, we can use these wonderful materials. Okay, thanks again for this long weekend, and good night. Have a nice long weekend. Thanks. See you next time.
Thank you.
Thank you, guys.
Okay, guys.